In the first 6 lectures of this course, we focused almost entirely on Einstein's theory of relativity. This included implications of relativity for black holes, gravitational waves, and even cosmology. Most people consider the theory of general relativity to be Einstein's greatest achievement, and one of the greatest scientific theories of all time. But if general relativity is the greatest physical theory of the 20th century, then quantum theory is a close second. You may recall from Lecture 1 that in 1905, a young and professionally unknown Albert Einstein published 4 absolutely groundbreaking papers. 2 of these papers proposed and established the special theory of relativity, while a third provided the first empirical proof that matter was in fact made up of atoms. In this lecture, we'll be talking about Einstein's other paper from 1905. In that paper, Einstein offered a radically different view of the nature of light. And in doing so, he proposed and offered evidence in support of the idea that light doesn't only behave like a wave, but that it's also made up of individual pieces or particles. At the time, these pieces of light were called quanta, and today we call them photons. More than any other single paper, this paper of Einstein's represented the beginning of what would become known as quantum physics. At the time, Einstein had no idea how strange quantum physics would turn out to be. Without realizing it, he had opened a Pandora's box of quantum weirdness, forcing us to forever change the way that we think about matter and energy. In his exploration of relativity, Einstein made a number of missteps over the course of his career. In my mind, however, these mistakes don't take away from the incredible accomplishments that he made. But all the same, it is clear that Einstein reached incorrect conclusions, at least for a time, pertaining to black holes, gravitational waves, and to the expansion of the universe itself. When it comes to the subject of quantum physics, Einstein often found it difficult to accept the conclusions and consequences of this theory, even when the conclusions were strongly supported by the data and evidence. His intuition and his philosophical prejudices made it difficult for him to accept the quantum nature of reality. And ultimately, he never did come to fully accept the strange quantum nature of the subatomic world. In the 2 lectures that will follow this one, we'll talk about Einstein's objections and struggles with quantum physics. But in this lecture, we're going to focus instead on Einstein's role in establishing quantum physics. And this is an example of something that Einstein got very right. His 1905 paper on light quanta is a masterpiece of creative and well-reasoned physics, and would rightfully earn Einstein a Nobel Prize. Today, every textbook on modern physics discusses the results and implications of this paper. But before jumping right into Einstein's paper on light quanta, we need to go back a few more years, to 1900. At that time, Einstein was just finishing up his undergraduate degree, and his name was almost entirely unknown among other physicists. But that year would turn out to be very important for Einstein's future work. It was in 1900 that laboratory measurements began to reveal for the first time some of the stranger aspects of light. To some degree, everything radiates light. Hotter and larger objects radiate the most light, while colder and smaller objects radiate less. Furthermore, hotter objects tend to radiate light with higher frequencies than colder objects do. In the years leading up to 1900, many physicists thought that they basically understood the nature of light. From what they thought were essentially first principles, physicists calculated the spectrum of light that was expected to be radiated from an object of a given temperature. This resulted in something known as Wien's law, named after Wilhelm Wien, who first arrived this equation in 1896. At high frequencies, Wien's law is fairly accurate. But in and around 1900, measurements began to show departures from this predicted spectrum, especially at low frequencies. Now remember, this equation had been derived from essentially first principles. By this I mean that in carrying out his calculation, Wien had assumed only very established laws of physics. It wasn't a controversial result in the least. And there was every reason to think that this equation should be correct, but yet somehow it wasn't. It was at this point in time that the great German physicist Max Planck stepped in. He started by experimenting with various mathematical expressions, until he found one that could match the observed shape of the spectrum. Generally speaking, this is not the way that physicists like to approach a problem. We'd much rather start with a set of principles and derive the correct solution. Instead, Planck had reverse engineered the underlying equation using brute force. And even though Planck did eventually find an equation that matched the data, even this wasn't very enlightening. Planck knew he had the correct equations, but he didn't know why the equation was the way it was. Furthermore, he didn't understand why Wien's approach to the problem resulted in the wrong answer. Planck knew what the right equation was, but he didn't know why. So with his new equation in hand, Planck set out to try to understand it. He started from the equation itself and began working backward, trying to figure out which of Wien's assumptions he would have to change in order to derive the correct equation. After some experimentation, he eventually found a way to do this. He determined that the measured spectrum of radiation could be explained if he made the following rather surprising assumption. To get the correct spectrum, he had to assume that the light emitted from a given object is composed of a finite number of discrete pieces. And each of these pieces of the light wave must contain a quantity of energy that is strictly proportional to the frequency of the light. Now at the time, neither Planck nor anyone else thought that this assumption could be justified on any physical grounds. From Planck's perspective, he was desperate to explain the shape of the observed spectrum, and making this assumption was the only way that he could find that seemed to work. As for what this really meant about the nature of light, Planck took a very conservative position. To him, the idea that light consisted of discrete parts or pieces was only a mathematical convenience. And according to Planck, this result did not have any bearing on the physical nature of light. If it had any meaning at all, Planck imagined that perhaps atoms might vibrate in a way that only emitted quantities of light proportional to their frequency. But again, that said nothing about light itself, only about the behavior of atoms. Between 1900 and 1905, little or no progress was made in advancing our understanding of light, or interpreting the meaning of Planck's strange result. That is until Einstein's paper on the subject. Unlike Planck himself, Einstein took very seriously the hypothesis that light might be made up of discrete pieces, or quanta as they were known. In his paper, Einstein not only argued that the existence of light quanta was a viable hypothesis, but demonstrated that this hypothesis could explain a number of other recent experimental results. One of the experimental results that Einstein brought up in his paper had to do with fluorescence. It was known at the time that certain kinds of materials would sometimes radiate visibly when they were exposed to light. And furthermore, it had been noticed that the frequency of the incident light was always higher than the frequency of the light emitted through fluorescence. This fact was known at the time as Stokes' rule, but before Einstein there was no understanding or known explanation for why this was true. It was thought that only the properties of the fluorescing material itself would determine the frequency of the emitted light. The frequency of the emitted light shouldn't have anything to do with the frequency of the incident light. But Einstein argued that in order for a given molecule to emit a photon of a given energy, it first must be struck by a photon with at least that much energy. If light consists of pieces, which each have an amount of energy proportional to their frequency, Stokes' rule would not be surprising. In fact, within this context, it made perfect sense. Next, Einstein's paper went on to consider and interpret an experimental result known as the photoelectric effect. I think it's probably fair to say that this was the most important part of Einstein's paper, and it was the part that did the most to advance the hypothesis that light is made up of discrete pieces, or quanta. It had been noticed previously by other physicists that when light is directed onto a metal surface, it can cause energetic electrons to be emitted from the metal. If hooked up to a circuit, these energetic electrons can even generate an electric current, known as a photocurrent. It had also been noticed that only high-frequency light seemed to be capable of generating a photocurrent. But no one prior to Einstein had figured out why. To better understand this result and how surprising it is within the context of traditional pre-quantum picture of light, let's take a moment to consider what a light wave really is. Regardless of what kind of wave we're talking about, the amount of energy that is carried by a given wave is proportional to the square of the maximum amplitude of that wave. The amount of energy carried by a water wave, for example, is proportional to the square of its maximum height. And for a sound wave, the energy carried is proportional to the square of its maximum change in pressure. A water wave with a maximum height of 5 meters carries 25 times as much energy as a similar wave that's only 1 meter high. In many ways, a light wave is similar to these other kinds of more familiar waves. But in other ways, light is a very different kind of wave. Water waves and sound waves are each made up of groups of molecules moving together. Light, on the other hand, is an electromagnetic wave, which means that it's a moving configuration of vibrating electric and magnetic fields. The amount of energy that is carried by a wave of light is proportional to the square of the strength of its maximum electric field. Before Einstein, it was thought that the effects of light striking a piece of metal would be spread out over the material. And the effects would be the same regardless of the light's frequency. Only the total intensity of the incident light should matter. But now let's rethink how this would work if the light isn't a continuous wave, but instead consists of a finite number of individual quanta. To free an electron from a piece of metal requires a certain amount of energy. If you impart less than this minimum energy, the electron will remain bound to its atom and trapped in the metal. But if enough energy and momentum is imparted, the electron can be freed, and perhaps even be accelerated to high speeds. In Einstein's interpretation of the photoelectric effect, low-frequency quanta of light simply don't have enough energy or momentum to free electrons from their atoms. Low-energy quanta could strike a plate of metal all day long without generating any photocurrent. Only high-frequency quanta carry enough energy to break an electron out of its atomic prison. Consider the following analogy. You're driving down a country highway, and every few moments you notice that another bug has smashed into your windshield. This might dirty your windshield, but it certainly doesn't cause it to break or otherwise do any real harm. And it doesn't matter how many bugs you hit. Over time, you might run into hundreds of thousands of bugs, and your windshield will still be perfectly fine. But if you ever collide with even one bowling ball, your windshield will shatter. This isn't because the bowling ball has more mass. One bowling ball has about the same mass as a few 100,000 insects put together. But the bowling ball strikes your windshield all at once. According to Einstein, an individual quantum of light strikes only one electron. And if that quantum of light has a high enough frequency, then it will have enough energy and momentum to free that electron, creating a bit of photocurrent. But if the frequency of the light is too low, the electrons will remain bound, regardless of how many quanta strike the metal. In his paper, Einstein laid out some very precise predictions for how the photoelectric effect should work. For example, he predicted that there would be a linear relationship between the voltage around a circuit and the frequency of the light that would be required to generate the photocurrent. At the time, the data wasn't sufficiently complete to either confirm or refute the predictions that were put forth in Einstein's paper. But in the years that followed, experiments were conducted that beautifully confirmed many of Einstein's predictions. By 1915 or so, direct and detailed measurements had definitively confirmed the predictions made by Einstein in his 1905 paper. Although Einstein's 1905 paper on light quanta made quite a splash, most physicists were at least initially very reluctant to accept its conclusions. For many years, Einstein remained one of the few physicists who thought that light quanta were actually real. Many other physicists, including Max Planck, for example, agreed that the hypothesis of light quanta was useful and that it could be employed as an effective mathematical trick, but Planck and many other physicists didn't go much farther than that. And they certainly didn't think that light quanta were real physical entities. It might seem strange to you that physicists at the time were so resistant to the idea of light quanta. After all, around the same period of time, physicists were starting to accept the conclusion that matter is made up of a finite number of individual atoms. You might very well be asking yourself what it was about light quanta that made them so much more difficult to accept. The problem, as most physicists at the time saw it, had to do with the nature of waves. According to classical physics, by which I mean pre-quantum physics, all waves are the result of collective behavior. Water waves and sound waves, for example, are each made up of vast numbers of molecules. These collections of molecules move in patterns that collectively result in the formation and propagation of a wave. But according to Einstein, a light wave is fundamentally different from these other kinds of waves. Just consider a single quantum of light. Since this is just one object, there can't be any collective behavior associated with it. So according to classical physics, such an object can't behave like a wave. But in Einstein's interpretation, even a single quantum of light is itself a wave. It has a frequency, and it carries energy as it moves forward through space, just as any other wave does. So according to Einstein, light was, in some important respects, made up of waves, while in other ways, light seemed to be made up of particles. From a classical perspective, this didn't make any sense at all. And to most physicists at the time, it seemed downright absurd. One of the most important behaviors associated with waves is the class of phenomena known as interference. The basic idea behind the interference of waves is that when two waves are overlaid on top of each other, they can either enhance each other or cancel each other out. Two waves with peaks that align with each other will combine to form a bigger and more powerful wave. This is called constructive interference. But two waves that are perfectly misaligned can cancel each other out entirely. The peak of one wave combines with the trough of another to form nothing. This is called destructive interference. One of the best examples of destructive interference is found in the technology of noise-canceling headphones. These devices measure the spectrum of the background noise and then add an out-of-phase version of this background to the music that you're trying to listen to. This out-of-phase background noise doesn't merely cover up the original background noise that's present. By destructively interfering with the background sound wave, the background noise is erased. Interference is a phenomenon that is only experienced by waves, and objects that are not waves don't experience anything analogous to destructive interference. If I combine 10 marbles with another 10 marbles, I'll always have 20 marbles. But if I combine a water wave that has an amplitude of 10 meters with another water wave that has an amplitude of 10 meters, the result could be a wave with a height anywhere between 20 meters and 0, depending on to what degree their peaks and troughs align or misalign with each other. The thing that made Einstein's light quanta hypothesis so perplexing was that it showed that light is made up of individual particles, making them more like marbles than like waves. But somehow, they still behaved like waves, experienced the same kinds of constructive and destructive interference that other waves do. From early on, Einstein understood and appreciated the challenges that came up with his light quanta hypothesis, at least as well as most of his colleagues. By 1910 or so, it was clear to Einstein that in order to make sense of the combined particle and wave-like natures of light, classical physics would have to radically change. No one could tell you what the full quantum theory was going to look like. It would take decades for that theory to fully form and come together. But long before that, Einstein was already very aware that quantum physics was going to be very strange indeed. During the decade or so that followed Einstein's 1905 papers, Einstein devoted a great deal of his time and effort toward developing the general theory of relativity, as we discussed in Lecture 2. But during this period of time, the quantum revolution also slowly continued to move forward. This stage, however, had less to do with the nature of light and more to do with the nature of matter. As I've said earlier, Einstein helped to establish the existence of atoms in one of his breakthrough papers in 1905. But physicists still didn't know what atoms really were, and they didn't know what they were made of or how they worked. Physicists who were trying to understand the nature of atoms didn't have a lot to go on during this period of time. Although experiments conducted by J.J. Thomson in 1897 resulted in the discovery of the electron, protons and neutrons wouldn't be discovered for years to come. During this period of time, the leading picture for how atoms are structured was what is called the plum pudding model. In the plum pudding model, an atom is basically an extended spherical blob of positively charged material with some negatively charged and stationary electrons distributed throughout it. The name of the plum pudding model comes from the fact that the electrons are distributed throughout an atom the way that raisins are throughout a plum pudding. For a couple of different reasons, something like the plum pudding model seemed like a logical guess for the structure of atoms, at least at the time. For one thing, most atoms are electrically neutral, So there had to be some positively charged material present to balance against the negative charge of the electrons. And second, moving charged particles were known to radiate light and lose energy very rapidly. By maintaining that electrons and atoms are stationary, as they are in the plum pudding model, it allowed them to retain their energy, thus making it possible for atoms to be potentially stable. But as it turns out, the plum pudding model does not provide a very good description of how atoms are really structured. In a series of experiments carried out between 1908 and 1913, physicists working under the supervision of Ernest Rutherford demonstrated that the positive charge in atoms is not distributed diffusely like it is in the plum pudding model. Instead, the positive charge is highly concentrated around the atom's center. This seemed to support an atomic model that resembled something more like a solar system, with a massive positively charged nucleus orbited by lighter and negatively charged electrons. But unlike in the plum pudding model, atoms in this solar system-like model seem to be inescapably unstable. Just like planets have to keep moving in order to not fall into the sun, the electrons had to be in a constant state of motion. And this meant that the electrons should all be radiating light and continuously losing energy. This loss of energy would cause the electrons to almost instantly collapse into the nucleus of their atom. In this model of the atom, there seemed to be no way to understand how atoms could remain intact for so long, or for any length of time at all. In 1913, a young physicist named Niels Bohr proposed a very radical solution to this problem. Bohr was in Denmark, but he had studied in England under the supervision of Ernest Rutherford, and he was up on all the most recent developments in atomic structure. The model that Bohr proposed was in many ways similar to Rutherford's solar system-like model for the atom. But instead of treating electrons like planets bound in orbits around the sun-like nucleus, Bohr treated the electrons like they were waves. For simplicity, Bohr's model focused on the simplest of the atoms, hydrogen, which consists of just one electron around a positively charged nucleus. Furthermore, he required the waves that represented the electron to follow circular paths around the atom's nucleus. Bohr's model solved at least two important puzzles related to atoms. First of all, it explained how atoms could be stable. Recall that because of its electric charge, a particle like electron will radiate light as it moves around a nucleus, losing energy rapidly and causing its orbit to almost immediately collapse into the atom's nucleus. But this fate could be easily avoided in the Bohr model. Unlike particle orbits, stable waves can only take on certain specific configurations. To help visualize this, picture a string that is vibrating in a stable pattern, maybe a string on a violin or a guitar, for example. The largest possible wavelength that a string can vibrate at is a wavelength equal to twice the length of the string. In other words, the lowest harmonic that this string can generate is one in which the full wave of the vibration extends all the way down the string and back again, back to where it started. The second harmonic is one in which two full wavelengths of the vibration are extended over the same distance. And the third harmonic consists of three full wavelengths and so on. The point of this analogy is that waves can take on stable configurations only for wavelengths that are equal to the total distance vibrating divided by an integer. A string that is 1 meter from one end to the other and back again can maintain a wave with a wavelength of 1 meter, or 1/2 a meter, or 1/3 of a meter, or 1/4 of a meter, and so on. But nothing with a wavelength in between these values can persist. Now let's apply this reasoning to Bohr's model for the hydrogen atom. In the Bohr model, the electron behaves like a vibrating string. And like a string, this meant that the electron can only vibrate with specific wavelengths, the harmonics. In the context of the Bohr model, we call these harmonics the energy levels of the atom. If an electron is in the second energy level of its atom, it could transition into the first energy level by releasing energy in the form of light. And if it somehow gains some energy, it could move into the third energy level, or the fourth, or the fifth, etc. But once an electron moves into the lowest possible energy level, called the ground state, there is nowhere lower for it to go. A particle would continue to spiral inward until it collapsed into the nucleus. But this couldn't happen to a wave. This is the aspect of the Bohr model that ensures the stability of the atom. And there is another major success of the Bohr model that we haven't talked about yet. For decades, physicists had known that various gases exhibited strange features in the spectrum of light that they emitted. This was especially true when the gases were heated to high temperatures. For each gas, light is emitted at very specific frequencies. In the case of hydrogen, for example, bright spectral lines appear with wavelengths of 656 nanometers, as well as 486, 434, 410, and 397 nanometers, among many others. But no one at the time had any idea where these numbers were coming from. Why or how atoms generated light with these particular wavelengths was a complete and total mystery. But Bohr's model has a clear answer to this question. Because the electron in a hydrogen atom could only exist in certain stable configurations, its transition from one energy level to another would only release specific calculable quantities of energy. Using his model, Bohr calculated the wavelengths of the light that should be emitted from hydrogen, and found that these results generally agreed pretty well with the observations. Further refinements over the next decades would be needed in order to dot all of the I's and cross all the T's, but more or less Bohr's model was basically able to explain the bulk of these and other measurements. So in summary, in 1905, Einstein had taken light, long thought to be a wave, and shown that it is made up of individual quanta, or particles of light. And now, most of a decade later, Bohr had demonstrated that electrons do not only behave like particles, but they also experience interference in the same way that waves do. At the atomic and subatomic scales, nature did not seem to consist of simple waves or particles, but instead both light and electrons seem to consist of a weird fusion of the two. Over the next 2 lectures, we're going to talk about how quantum physics developed in the 1920s and beyond. We'll also talk about the meaning and interpretation of this new theory and the role that Einstein played in the ensuing discussion and debate.